Okay, let's continue our discussion of the log function. You'll remember that if we have a positive number a greater than 1, then we know that the graph of the log function, base a, looks a little like the following. Here's my x-axis, here's my y-axis, and we're going to look at the graph of the equation y equal the log base a of x. Then here at this point, x equal 1, we know the value of the log base a of 1 is 0. And we'll say that a is some point out here. Then the value of the log base a of a, that's equal to 1. So we have a curve that goes through these 2 points, and then as the values of x approach 0, they get closer and closer to 0, the values of y, which are equal to the log base a of x, those values approach minus infinity. So we have an asymptote along the y-axis in the negative direction. And of course, the domain of the log function is the set of positive numbers. So the domain of the log base a of x, this is equal to the interval 0 to plus infinity. All right, and I'm going to mention that if a happens to be a positive number between 0 and 1, then the graph of our log function looks a little like this. So we're looking at the log base a of x in the case where a happens to be a positive number, less than 1. Then again, the log base a of 1, this is equal to 0. And the log base a of a, this is equal to 1. Okay, so we'll say this is the point A. Here's 1. We know the graph is going to pass through this point, and because we chose A to be between 0 and 1, the value of A lies somewhere in this interval. And here I'm just indicating it by this arbitrary point. And the graph of our log function in this case looks like this. Now, the way I've drawn these, it almost looks like there's an asymptote as x goes to plus infinity, but that doesn't happen. Let me write that down here. The limit as x goes to infinity of the log base a of x, this is equal to, well, look, this curve just keeps on decreasing. And it actually decreases to minus infinity. It does so very slowly. And up here, I'm going to write the limit as x goes to infinity of the log base a of x. This is equal to plus infinity. So our graph, our graph continues growing, continues increasing without bound. As x gets bigger, the values of y keep on getting bigger and bigger, and there's no bound. So there are no horizontal asymptotes. The asymptotes are just the vertical asymptotes. Now, the log function satisfies some very interesting identities. And so that's what we're going to play with now. Let me remind you of one other thing. If I say the log base a of x is equal to y, remember, this is equivalent to saying that a to the y power is equal to x. Okay? So this is our inverse relationship. This is over here. This is the exponential function, base A. And over here, this is our log function, base A. And they're inverses of one another. Another way of writing this is to write that the log base A of A to the x power is equal to x. Or I could write A to the log base A of x. This is also equal to x. So these are our basic identities satisfied by the log function. Log base A function. All right, let's look for a couple more. So one of the most fundamental identities that the log function satisfies, log base A, is the following. It's the log base A of x times y. So x and y here have to be positive numbers. So x, y greater than 0. This is equal to the log base A of x plus the log base A of y, right? So let's prove this. I think this proof really helps you to understand how the log function actually functions. So what I'm going to do is I'm going to set u equal to the log base A of x, and I'm going to set v equal to the log base A of y. Okay? So I'm just calling the log base A of x, I'm calling it u. The log base A of y, I'm calling it v. Now, we know from this identity up here, this identity here, that if I have the log base A of x equal to u, which I have here, this is equivalent to writing. So this is equivalent to writing that x is equal to a to the u power. And over here, this is equivalent to writing y is equal to a to the v power. Okay? So let's do something. Let's look at x times y. Okay, going to look at x times y. And I know that this is equal to, well, x is equal to a to the u power, and y is equal to a to the v power. So x times y is equal to a to the u times a to the v, which is equal to a to the u plus v power. Got it? All right. Now, the log base A of x times y is equal to, so I'm just taking the log of both sides of this equation here. So I'm looking at the log base A of x times y. This is equal to the log base A of a to the u plus v power, right? But what do we know? We know we have this basic identity here, that the log base a of a to the x is equal to x. So let's use that down here. So here I have the log base a of a to the u plus v power. Well, that's got to be equal to u plus v. And this in turn is equal to the log, well, u, what did we do? We said u equal to, where was it? Here it is. U is equal to the log base a of x, base a of x, and then v is equal to the log base a of y. And there we have it. Our identity is proven, okay? All right, there's another very useful identity that we need to take a look at, and that's the following. The log base a of x to the y power. Okay, x to the y power. Now here, x has to be positive. X is positive, but y can be any real number. This is equal to, so our identity is this. This is equal to y times the log of a to the x power. Okay, so we have the following very, very important identities, and these you really have to commit to memory, and you have to be able to use these. So what do we have? We have, let's start at the beginning. We have the log base a of x is equal to y. This is equivalent to saying that a to the y is equal to x. So this is a basic definition, really, of the log function, because it's the inverse of the exponential function base a. Then we have the log base a of 1 is equal to 0, and the log base a of a is equal to 1. We have that the log base a of x times y is equal to the log base a of x plus the log base a of y. And then we have the log base a of x to the y power is equal to y times the log base a of x. All right, and again, let me remind you, in this identity, x and y have to be greater than 0. Otherwise, these logs on the right-hand side of our identity are undefined, because we can't take the log of a negative number. And here, x has to be positive. So x has to be positive because I'm taking the log of it again on the right-hand side, but y can be negative. So y can be any real number. Let me write it like y is any real number. So in particular, if I have the log base a of x to the negative 1, this is equal to minus 1 times the log base a of x. All right. Well, let's do some calculations. Let's look at some related problems. So let's look at the following. Let's take the log base a. So this is an example. The log base A of x squared divided by y times z to the third power. Okay? And what I want to do is I want to expand this expression in terms of the log base A of x, the log base A of y, and the log base A of z. So let's see how we might go about doing that. What I'm going to do is the following. I'm going to write the log base A of x squared divided by y times z cubed. I'm going to write this as the log base A of x squared. Now, 1 divided by y can be written as y to the negative 1 power, right? So let's recall 1 over y is equal to y to the minus 1 power. So I'm using that to write 1 over y as y to the minus 1 power. And then I have 1 over z cubed, and that's equal to z to the negative 3 power. So this is z to the negative 3 power. Okay. Now what do I know? Well, I can write this since on the right-hand side, the terms inside the parentheses, that it's represented by a product. That term is represented by a product. This is going to be the log base A of x squared plus the log base A of y to the minus 1 times z to the minus 3. And this in turn is equal to the log base A of x squared plus the log base A of y to the minus 1 plus the log base A of z to the negative 3 power. Okay, so what I've done is I've taken the log of this expression and I've written it in terms of the log base A of an expression just involving the variable x, over here just involving the variable y, and then the third term just involving the variable z. So in order to do that, what I used was this identity. And now what we're going to do is we're going to use this identity. All right? So on the three terms that we have, sitting here, what we're going to do is we're going to bring these exponents outside the log. So I'm going to write this first term as 2 times the log base A of x. Here this is minus the log base A of y, and then plus negative 3 times the log base A of z. Okay. So again, this is 2 log base A x minus log base A of y minus 3 times the log base A of z. Right? Let's try another one. What should we do here? Let's try this one. The log of x divided by the cube root of the cube root of 1 minus x. Okay? First of all, notice there's no base there. Remember, what does that mean? What is the base? Well, if the base doesn't appear on the log, then it is assumed that the base is equal to 10. So we're dealing with a common log here. All right? Now, okay, so what can I do? I can write this as follows. I can write this as the log, and again, base 10, but that's understood, of x times, now what is? So let's think about this. What is 1 divided by the cube root of 1 minus x? How can I write that in terms of exponents? Well, this is equal to 1 over 1 minus x to the 1/3 power. And this in turn is equal to 1 minus x to the minus 1/3 power, right? So I'm going to write this expression as the log of x times 1 minus x to the minus 1/3 power, all right? So this was a little bit of computation that's kind of an aside. And now let's look at this. So here I have the product of x with this expression here. So I can write this as the log base a, or the log base 10 rather, of x plus the log base 10 of 1 minus x to the minus 1/3 power. Okay, that's kind of nice. And then I can write this as log of x. And here I have the log of something being raised to the minus 1/3 power. So by our second identity that we looked at today, what I can do is I can pull this exponent in front of the log, and I can write this as minus 1/3 times the log of 1 minus x. And now you might be really, really tempted to go a little bit farther with this. All right, but don't be deceived. This is it. We can't simplify this. We can't expand this out anymore. One of the things that a lot of people get wrong is they think that there's an identity of the following form. That the log base a of x time or x plus y, a lot of times they write this as the log base a of x plus the log base a of y. And this is not true. Doesn't work, okay? So that's why we can't proceed any farther here. Because if I could, then I'd be taking the log, look what would happen. I'd be taking the log of 1 plus the log of minus x. But if I'm assuming that x is bigger than 0, then minus x, that would be negative. I'd be taking the log of a negative number, and that just wouldn't make any sense. Okay. So this is our final answer. All right, let's take a look at another problem. Suppose we look at this. We have let's see, what should we do here? 2 times the log base 5 of x plus 2 times the log base 5 of y minus 3 times the log base 5 of z. Okay, what can I do with this? So here, what I want to do is I want to combine this. So before we wanted to expand out the log of an expression, here we want to combine into a single log expression. In other words, we want to write this as the log base 5 of some quantity in here. Okay, and so what we have to do is figure out, hey, what goes in here? All right, this is going to be, so I'm looking at this top expression, and this is equal to 2 times the log base 5 of x plus 4 times the log base 5 of y minus 6 times the log base 5 of z. And this in turn is equal to the log base 5 of x squared. So now what I'm doing is I'm bringing this coefficient and I'm making it an exponent on x. Just as I'm going to take this coefficient and I'm going to make it an exponent on y, and this coefficient, and I'm going to make it an exponent on z. So this is going to be plus the log base 5 of y to the 4th. I'm going to change back to the black ink, plus the log base 5 of z to the minus 6 power. Okay, so we have, this is the log base 5. Now what I can do is I can combine these. See, it's the log base 5 plus the log base 5. If I add those together, that's the same as taking the log base 5 of x squared times y to the 4th plus the log base 5 of z to the minus 6. And now I can combine these two. So this is going to be the log base 5 of x squared times y to the 4th times z to the minus 6 power. And this I could write as the log base 5 of x squared times y to the 4th divided by z to the 6th power. Okay. Pretty straightforward, huh? Let me show you another. One more identity, all right? So, suppose I have a number x greater than 0, and I'm looking at the log base a of x and the log base b of x. How are these related? So how are these logs related? It turns out that there's a very nice relationship between these, and this is called the change of base formula. And it goes like this. The log base a of x is equal to the log base b of x divided by the log base b of a. Okay? Should we prove that? Let's try. Let's see what we can do with this. Okay? So let's look at the log base a of x. And we'll do as we did before. We're going to set this equal to, let's set it equal to u. Okay? It's equal to u. So we're going to set the log base a of x equal to u. We know because the log function base a happens to be the inverse of the exponential function base a. We know that this is the same as saying that a to the u power is equal to x. All right, so here I'm going to write that again. X is equal to a to the u power. And now what I'm going to do is I'm going to take the log base b of both sides of this equation. So I'm going to apply, let's put it that way. I'm going to apply the log base b to both sides of this equation. So when I do that, I get the following. The log base b of x is equal to the log base b of a to the u power. And the log base b, so we had something that kind of looks, if you look at this, it looks like, gee, this might be kind of tough to prove. But in point of fact, this is very easy. So I have the log base b of x. Here, what do we have? Here we're taking the log base b of a to the u power. I'm going to bring that u out in front. So I'm going to write this as u times the log base b of a. Okay. And then I'm going to write this as the log base b of x divided by the log base b of a. And this is equal to u. But what was u equal to? U is equal to the log base a of x. And now we're done. We proved it. Kind of nice, huh? We should make mention of the fact that that a here, because it's a base, a is not equal to 1. Because if it were, then we'd be in trouble because we'd be dividing by 0. So we don't want to do that. All right. Let me see if we can find a problem that involves this. So it says here, okay, so it says here, change the log base 5 of 2 to the natural log function. So in other words, what I want to do is I want to write the log base 5 of 2 in terms of the natural log function. And remember, the natural log function, this is denoted by ln. So this is equal to, well, this is equal to ln of 2, okay, ln of 2, divided by what? Ln of 5, okay? Don't make this mistake. So I see this a lot. Don't write this. This is not equal to the natural log of 5 divided by 2. This is that would be that's a serious mistake. Okay? This is just ln of 2 divided by the log of 5. This is not equal to the log of 2/5. And if you wanted to go further with this, you could approximate this. So one could approximate using a calculator. But that's all you're doing. So when you plug this into a calculator, you're only approximating it to, say, 10 decimal points. All right, let's leave it there. And what do you have? You have an exam coming up this week. So exam this week. All right. And you have homework. And I think that homework is due on the 12th. All right. Now, look at the suggested problems in the syllabus, okay? And remember, we're not going to test over 4.4, okay? So this material that I presented just now, we're not going to test over it, but you really got to know it, so study it this week, okay? Okay, and good luck with your